Assalamu alaikum dear students. I welcome you to 30th lecture of probability and stochastic processes. In previous lecture, we finished our discussion of diagonalization of covariance matrix of two random variables in order to design a linear transformation which takes a pair of correlated random variables and gives a pair of uncorrelated random variables. This diagonalization was done through usage of eigenvalues and eigenvectors. After that, we moved to discussion of random vectors or vectors of random variables where we observed more than 2, 3, 5, 10, 20 or any finite number of unpredictable values, and these values were assumed to be generated by a vector of random variables. So the observed values formed a vector because we did not want to confuse a certain observation with another one. So every observation had its proper place, thus we had a vector. So observed vector was denoted by small letter x, which was equal to x1, x2, x3 all the way up to xn. And these values were assumed to be generated by a vector of random variables denoted by capital X, which was equal to capital X1, comma capital X2, X3 all the way up to xn. We talked about different characteristics of random vectors like joint PDF, joint CDF and transformation. Actually, the pair of random variables that we studied in previous lectures in substantial detail also belong to the class of random vectors. If you are taking just a pair, just two random variables, then length of vector is 2. But in general, length of vectors of observed values can be more than 2, and you can deal with more than 2 random variables at the same time by forming a vector of random variables or a random vector. So whatever we said about pair of random variables is also applicable to random vectors. In particular, if we have a random vector of length capital N, we can form a function which is from a space of n-dimensional real numbers to scalar values, and that function can be made to be joint PDF of random vector if it fulfills certain requirements. Similarly, we can form a function from Rn to R1 which is joint CDF of random vector with some conditions that it must satisfy, including that the maximum value of the function should be 1. Similarly, if we have a joint PDF for a random vector of length n, we can form marginal densities for all elements in the random vector. These marginal densities will be functions from R1 to R1. And we can also form marginal densities for pairs of random variables by picking any two random variables from a long random vector. These marginal densities will be functions from R2 to R1. We can form other marginal densities which are functions from r raised to power k to R1, where k is less than n, the length of the random vector. We can use these marginal densities to find all types of expected values. If we are using marginal densities of individual elements of random vectors, we can find the mean, the variance, the second moment and other moments of individual elements in the random vector. If the marginal densities that we have are functions from R square to R1, that is they are joint densities of two elements of random vector, we can find the covariance between the two random elements of the random vector. We can transform this random vector to another random vector using linear or non-linear transformations. In that case, we can even find the joint PDF of the transformed random vector. But usually these calculations are very complex and we don't do that. One transformation that I told you was important and we were going to discuss it more detail was the transformation from a random vector to a scalar value, where we form the transformed random variable z as sum of all the values of all random variables in the random vector. So if we have a length n random vector and we observe n unpredictable values, we will form the transformed random variable z by summing all the observed values to get the value of z. This transformed random variable is important because it is used in sampling of large populations to find the statistical relevance of the sample and the whole population. It has other applications also in pattern recognition and other areas where we observe more than two values as the outcome of our experiment. In last lecture, we started talking about finding the PDF of this transformed random variable, which is sum of all the elements in a random vector. Let's continue with our discussion, and we will start with a simple case, a case which is a revisit to the problem we already solved, that is finding the PDF of sum of two random variables. So we'll start with two random variables and then we'll extend our discussion to n random variables, and the idea is to find the PDF of transformed random variable, which is sum of a finite number of independent random variables. So let's start with sum of two independent random variables and its PDF. The two underlying random variables could be x and y, or they could be x1 and x2, or they could be from a collection of x, x1, x2, x3, xn, where all of these are independent and identically distributed. If that's the case, we can use PDF of x, one of them, to represent PDF of x1, x2, x3, all of them. So here we are trying to find the PDF of transformed random variable z, where z is equal to x1 plus x2 or x plus x. But please note, if I say x plus x, do not consider this as an algebraic expression, sum the two x's and say z is equal to 2x, because the transformation z is equal to 2x is different from the transformation z is equal to x1 plus x2, which is simply said x plus x. Take an example. If you throw a dice and you consider the outcome of dice as random variable x, then x takes on values 1, 2, 3, 4, 5, 6 with equal probabilities of 1 over 6. Then you transform this observed value using the transformation z is equal to 2x. Then random variable z will have values 2, 4, 6, 8, 10 and 12 with equal probabilities of 1 over 6. All you are doing is just multiplying 2 with the observed value. Now roll two dice. They are identical. They follow the same probability model. So instead of saying the observed value first being x and observed value second being y, we can say x and x, and in that case the sum of two random variables will take on values which lie between 2, 3, 4, 5, 6 all the way 12 with unequal probabilities. So if z is equal to x1 plus x2 or x plus x, it's not equal to z is equal to 2x. So we are interested in finding the PDF of sum of two independent random variables which have the same PDF. So we are saying z is equal to x1 plus x2 or x plus x. We are not making any assumption about particular function which is the PDF of this collection of random variables x, x1, x2, x3. It can have any valid expression for its PDF. So with that assumption that it can have any general expression which is valid for its PDF, we are going to find the PDF of transformed random variable z, where z is equal to x1 plus x2 or x plus x or x plus y, whichever way you want to consider. To find this PDF, we have to integrate the regions of xy plane or x1, x2 plane in appropriate manner so that we can find the CDF of z. And once we have found CDF of z, we can find the PDF of z by differentiating it with respect to the parameter z. So we are going to find the CDF of z by integrating this joint PDF, which is defined over the whole plane in an appropriate manner. And the appropriate manner is that you take a certain value of parameter z and see for all the pairs of x comma y or x1 comma x2 which give a sum which is less than this value of parameter small z, and integrate all those points x comma y to find a number which will be a probability, which will be the value of CDF of z at that particular value of the parameter small z. Let's have a look how this region is going to look like. If this is the 2D plane over which the joint PDF of two identically distributed random variables is defined, then we are going to take a line which is y plus x is equal to z, or y is equal to x minus z. Then all these pairs of points x comma y which are to the left and below this line will contribute to the probability which will give us the value of CDF of z for that value of small z. Please note that this red region shown here goes all the way here, all the way here, and all the way here. It covers all parts of second, third and fourth quadrant which are below and to the left of this line with an orientation of 135 degrees with respect to x-axis. So with this area to be integrated, we will find a double integral, and that double integral will be for small strips which start here and go all the way to minus infinity, and all the strips from minus infinity to plus infinity. When you evaluate this double integral, it will give you a number that will be value of CDF of transformed random variable z for the value of small z, the parameter which defines the line, the location of line with orientation of 135 degrees. Once you have fz, the CDF of z, as an expression of small z, you can differentiate it with respect to small z to get the PDF of transformed random variable z, which will also be a function of z. Let's have a look at the evaluation of that double integral and its differentiation with respect to small z to get the PDF of random variable z. As you can see on your screen, that the PDF of z is equal to differentiation with respect to z of the CDF of z. The CDF of z has a long expression which is obtained through the double integral of the region that I just showed you in the previous slide. So if you take differentiation of this long expression in square brackets with respect to z, you will get the PDF of z. Since random variables x and y are independent, we can factor this joint PDF into PDF of x and PDF of y and take out the PDF which is not required in the inside integral. You will get this expression shown on the next line, and this expression shows that the inner integral is equal to CDF of x with a value of z minus y. So this internal expression shown in curly braces is equal to the CDF of x with value z minus y. Now, if everything is nice and finite, you can switch the order of this differentiation with this inner integral, and you will get this expression which tells you that PDF of z is an integration where first you will write inside the integral the PDF of y and then differentiation of CDF of x with value z minus y, and this differentiation will be with respect to z. If you evaluate this differentiation first, you will see that this expression in the square bracket is nothing but PDF of x at value z minus y. So everything simplifies to this nice integral, which is integration from minus infinity to infinity of PDF of y multiplied by PDF of x, where the argument is replaced with z minus y, and the whole thing is integrated with respect to y. This integral on the last line is also called the convolution integral, and it is represented by the two PDFs involved in the integration and a star in between the two PDFs. So this convolution integration is denoted by PDF of x star PDF of y. So if you have two independent random variables x and y, you want to find the PDF of transformed random variable z is equal to x plus y. You can get the PDF of z by taking the convolution integral or by convolving the PDF of x with PDF of y. If x and y have the same PDF, which is equal to PDF of x, then we can say that if there are two random variables, both are independent and both have the same PDF fx, then you can find the PDF of transformed random variable z, which is sum of the two random variables, by convolving the PDF of x with itself. And this convolution gives you a new PDF. Now, if you want to find the PDF of a transformed random variable z, which is equal to sum of three independent random variables, you can find the PDF of z by first convolving the two PDFs. That will give you PDF of z, and then assuming that you are adding another random variable of the same type, you can convolve this result of convolution of two PDFs with the third PDF, or you are convolving three PDFs which are same. So if z is equal to x plus x plus x, the PDF of z is convolutions of three PDFs of x, fx convolved with fx convolved with fx. And you can extend this argument. So if you have n independent random variables x1, x2, x3, xn, they have the same PDF as another random variable x, then the PDF of transformed random variable z, which is equal to sum of x1, x2, x3, xn, is n-fold convolution of PDF of x. That is the nice part of having independent random variables and having a simple convolution that gives you the PDF of sum of n independent random variables. When you convolve PDF of one random variable with PDF of another random variable, you usually get a smoothing effect, and the extent of the resulting PDF is usually larger than the original PDFs. So let's have a look at a few simple cases. If I have a random variable x which is uniformly distributed over a finite range, which could be from a to b, minus a to a, minus 10 to 10 over any finite range. If this is the PDF of random variable x that I start with, then this is the PDF of sum of two random variables x plus x. So if you sum two random variables, they are independent, the PDF of both of them is this uniform, then the PDF of transformed random variable z, which is equal to sum of the two independent random variables, will be triangular in shape. And if you take three such independent random variables, then z is equal to x plus x plus x, or sum of three identical independent random variables with all of them having this PDF. The result is this. This PDF is a polynomial of second degree, and this represents the PDF of sum of three identically distributed independent random variables. Going further, if we take z to be sum of 5 independent and identically distributed random variables, this is the shape of the PDF that you get. This is going to be a polynomial of degree 4, and remarkably, its shape is very similar to the shape of Gaussian distribution. Gaussian distribution has a bell-shaped curve with long tails. So you saw that if you start with a random variable which is uniformly distributed and keep adding this type of random variable to form a transformed random variable z, then as you add more such independent random variables to form z, the shape of PDF of z becomes smoother, becomes elongated, and its shape approaches a bell-shaped curve, which is characteristic of Gaussian random variable. So we can make a guess that if you add a lot of independent random variables, then the shape of the PDF of sum of all these random variables will approach a Gaussian distribution. Actually, this is indeed the case, and we are going to cover this in coming lectures. We saw that if we have a collection of independent random variables and we have a new random variable by adding all the values of these random variables, then the PDF of this transformed random variable, which is sum of these random variables, is equal to convolution of PDFs of all the random variables involved. There is another way to reach this conclusion. There is another way to address this transformation of addition of a finite number of random variables, and that is through characteristic function. A characteristic function is a special expected value of a random variable. When we were dealing with random variables, we dealt with their mean values, their second moment, their centralized second moment, which is variance, and other higher moments. These moments were obtained by taking the expected value of a function of underlying random variable. If we use the underlying random variable itself, then in the integral we used x times PDF of x, and we integrated it to get a number which was the mean value of random variable. If we wanted to find the second moment, we used x square PDF of x and then integral. If we wanted to find variance, then we used x minus mean value of x whole square multiplied by the PDF of x, and then we integrated. So we can use any function of random variable x, multiply it with PDF of x, integrate to get the expected value of the function that we used in the integral. So we can use any function of x. We can use x square to get second moment. We can use x minus mu x whole square to get variance. Can we use 2 raised to power x? Instead of using x raised to power 2, can we use 2 raised to power x? Certainly. That expected value will be expected value of 2 raised to power x. It does not have a name like variance or other more well-used name, but it will give you expected value of 2 raised to power x. Can we find expected value of e raised to power x? Yes, certainly we can find, and that will give you another number. All these functions when evaluated give you a scalar valued number. So mean, variance, second moment, expected value of 2 raised to power x, expected value of e raised to power x, all when evaluated give you a scalar valued number, which is the expected value of the function used in the evaluation. If we used e raised to power j times x, where j is complex number, square root of -1, then this evaluation will give you expected value of e raised to power jx, but it's going to give you a complex result. It will be a number with real part and imaginary part. But if you introduce a certain parameter in this equation, say instead of using simply a function of x in the evaluation of expected value, you use a function of x and another parameter. So parameter can be alpha, beta, omega, delta, whatever. So the function is function of two parameters, x and another external parameter that you introduce. So when you use that parameter in the evaluation and you evaluate the integral by putting that function of two parameters, putting the PDF and taking the integral, the parameter is going to survive. The resulting expression will be a function of the new parameter that you introduce. So here the expected value of this function of two variables x and a new parameter will be a function of parameter. And this is how we use characteristic function. Characteristic function of a random variable x is equal to expected value of e raised to power j times omega times x. So by introducing omega, we will get an expression, not a number, not a real valued number, not a complex valued number, but a complex valued expression which will be a function of omega, the new parameter that we introduced. The question is, why we go to such lengths and why we introduce this j and omega to find expected value of a complex expression? The answer is that we do this complicated evaluation so that we can compactly represent some other complex relationships between random variables and other quantities of interest. This type of expression e raised to power j omega x is usually used in harmonic analysis of signals. So here we are taking PDF of x and putting e raised to power j omega x next to it and then integrating it. Then we are searching for some harmonic content in the PDF of x, and the resulting expression has some nice characteristics that we are going to use to find the PDF of sum of a finite number of independent and identically distributed random variables. Before we use the characteristic function to find the PDF of sum of a finite number of independent random variables, let's have a look at a few simple cases of random variables and their characteristic functions. The first case is the characteristic function of a uniformly distributed random variable. So if the random variable is uniformly distributed over an interval which starts at -a and ends at a, then all expected values will use integration from -a to a. And this is the function of random variable x that we are going to use for evaluation of characteristic function. Please note that this factor 1 over 2a is height of the PDF because PDF is of a uniformly distributed random variable over an extent which is of length 2a from -a to a. Hence, this is the height of the PDF. This should have been inside the integral, but this is a constant. I can certainly take it out. And then if you simplify this integral, you get a simple expression of sine of omega times a divided by omega. Please note that in this case we used a symmetric PDF. The PDF of uniformly distributed random variable started at -a and ended at a, and it was a flat in this region, so it was symmetric about y-axis. Due to this symmetry, the expression for characteristic function of uniformly distributed random variable comes out to be a real valued expression, even though we started with finding the expected value of e raised to power j omega x, which is a complex valued quantity, but due to symmetry of the PDF, the result comes out to be a real valued expression. This will be clear if we take the next case. The next case is a random variable x which is exponentially distributed with parameter lambda. So if random variable is exponentially distributed, this is the PDF lambda times e raised to power minus lambda x. Lambda is constant, I have taken it out, and I am trying to find the expected value of e raised to power j omega x again. If you simplify this integral, the result is lambda over lambda minus j omega. For this case of exponentially distributed random variable, the result is a complex valued expression, lambda over lambda minus j omega, because the PDF of exponentially distributed random variable is only defined for positive values of random variable x. So due to non-symmetry across y-axis, the result of expected value of e raised to power j omega x is equal to a complex valued expression. The last random variable that we are going to use to find the characteristic function is the Gaussian random variable. So for a Gaussian random variable which is normal with parameter 0, 1, that is it has mean value of 0 and variance has 1, the characteristic function is integration from minus infinity to infinity. This is the value that we use to find characteristic function, and this is the PDF of x, 1 over square root of 2 pi e raised to power minus x square over 2. If you simplify it by combining this e raised to power minus x square over 2 with this, completing the square, changing the random variable, and then making careful observations, you get a simple answer that the characteristic function of a random variable which is Gaussian with mean 0 and variance 1 comes out to be e raised to power minus omega square over 2. Once again, Gaussian is a symmetric PDF, and the value of the expression of characteristic function is a real valued expression, e raised to power minus omega square over 2. Please note that shape of this characteristic function as a function of omega is same as the shape of the PDF of x. If you ignore the constant 1 over 2 pi square root, then the shape of the PDF of x is also of the bell-shaped curve e raised to power minus x square over 2, and the shape of the characteristic function as function of omega is also bell-shaped curve e raised to power minus omega square over 2. So now that you have seen characteristic functions of a few simple random variables, let's try to use this characteristic function to find the PDF of sum of a finite number of random variables. For that, we'll take that convolution integral and see how we can combine the properties of convolution integral and the properties of characteristic function to come up with a simplified approach to find the PDF of sum of finite random variables. Once again, we'll start with a simple case of two independent random variables. If we have two independent random variables x and y, and we define z to be x plus y, then PDF of z is equal to convolution of PDF of x and PDF of y. If you want to find the characteristic function of this new random variable z, you can use the PDF of z, multiply it with e raised to power j omega z, integrate the whole thing, and you will get an expression of omega which will be the characteristic function of random variable z. But suppose you have not evaluated the PDF of z, but you have that convolution integral. So instead of using the PDF of z in evaluation of characteristic function, you can use that convolution integral. So here you can see on your screen that instead of using PDF of z, you can use convolution of PDF of x and PDF of y, which is given by a nice integral with respect to x. This can very well be an integral with respect to y, because x and y can play their roles in each other's place. So if you use this convolution integral instead of PDF of z, the characteristic function of z can be evaluated by multiplying e raised to power j omega z with the convolution integral and integrating the whole thing with respect to z. Since everything involved is a function of x or z, you can change variables and do other manipulations to come up with a final expression which is equal to multiplication of characteristic function of random variable x and characteristic function of random variable y. So if you have sum of two independent random variables as a new random variable, then characteristic function of sum of the two independent random variables is equal to multiplication of characteristic functions of the two independent random variables used to define the new random variable as sum of the two independent random variables. This can certainly be extended, and if you have sum of three independent random variables defined as new random variable z, then the characteristic function of z is equal to multiplication of characteristic functions of the three independent random variables used to define the new random variable as sum of the three independent random variables. And you can extend it to n random variables, and if all of the n random variables are independent and identically distributed, then characteristic function of z, which is sum of those n independent and identically distributed random variables, is multiplication of characteristic functions of the underlying random variables put together. And if they are identically distributed, their characteristic functions will be the same. Hence, the characteristic function of a random variable which is defined as sum of n IID random variables is equal to n times multiplication of characteristic function of one of the random variables used in the addition. So use of characteristic function allows us to replace the convolution integrals with simple multiplications, where convolution integrals use PDFs of the random variables involved, and the multiplication uses the characteristic functions of the random variables involved in the convolution. Let's see how this simplification, where convolution integral is replaced by multiplication, is going to help us find the PDF of sum of independent random variables. We'll start with a simple case of sum of two Gaussian random variables which are independent. If we have two Gaussian random variables independent of each other and a new random variable is defined as their sum, we can use the convolution integral, or we can use the joint Gaussian PDF and find CDF by taking integration as parameterized with small z and then take differentiation, or we can directly use the characteristic functions. Let's use the characteristic function. If we have two Gaussian random variables both independent of each other, then the characteristic function of z, which is sum of the two Gaussian random variables, is going to be multiplication of two Gaussian random variables. And if they have the same PDF, they are identical and independent, then we will have a characteristic function e raised to power minus omega square over 2 multiplied with e raised to power minus omega square over 2, and when you simplify this, this comes out to be e raised to power minus omega square. This characteristic function of sum of x and x, which is z, has the same shape as the characteristic function of x. Instead of e raised to power minus omega square over 2, we have 2 times omega square over 2, or simply minus omega square. So the exponent has increased its value from omega square over 2 to omega square, but the shape remains same. So you can see that the characteristic function of z gives us a clear hint that z is also a Gaussian random variable. It has 0 mean, but its variance is 2 instead of 1. And if you extend this argument further, you can see that if we have n Gaussian independent and identically distributed random variables, and you define z as a sum of those independent random variables, then characteristic function of z will be nth power of characteristic function of x, which is e raised to power minus omega square over 2. And if you take its nth power, it comes out to be e raised to power minus n times omega square over 2. Once again, shape of the characteristic function of sum of n Gaussian independent random variable is same as the shape of the characteristic function of one of them, or shape of a bell-shaped curve, or shape of Gaussian PDF. So if you add n Gaussian independent random variables, you will get a Gaussian random variable with variance which is n times the variance of one of the random variables used in summation. We saw that if we add a few Gaussian random variables which are independent, the result is another Gaussian random variable with different variance and possibly different mean value also. What about other random variables? If we have a uniformly distributed random variable or any other random variable, and we have a collection of such random variables, and we add the values to get a new random variable, what will be the PDF of the new random variable? Can characteristic function help us? It certainly can, and if the random variables are independent, we can make a certain educated guess about the shape of the PDF of sum of a finite number of those random variables. Let's take the example of uniformly distributed random variable. So we have x1, x2, x3 all the way up to xn, and another random variable x, and all of these have the same PDF, which is uniform over, say, -1 to 1. So if there is a collection of uniformly distributed random variables all having flat PDF from -1 to 1 with a height of 1 by 2, we can find characteristic function of one of them, which will be sine omega a, where a is 1 divided by omega, or sine omega over omega. If sine omega over omega is the characteristic function of one of the collection of uniformly distributed random variables, then if we define a random variable z, which is sum of a few of them, then characteristic function of z will be nth power. N is the number of uniformly distributed random variables that are added to get z. So the characteristic function of z will be nth power of sine omega over omega. Let's have a look at a few graphs which show how this sine omega over omega raised to power n behaves if we change value of n. This is sine omega over omega, or the characteristic function of random variable x, where x is uniformly distributed from -1 to 1. If you add two such random variables which are uniformly distributed, this is the shape of characteristic function of the sum of them. If z is sum of two uniformly distributed random variables, this is the shape of characteristic function of z. This is the shape of characteristic function of sum of three uniformly distributed independent random variables. And this is the shape of five uniformly distributed independent random variables. There is a difference. All these plots are from -20 to 20, but this plot has only taken the central part, so this plot is from -3 to 3. So if you look at the expanded version of this plot, which is the shape of characteristic function of sum of five uniformly distributed independent random variables, you can have a clear indication that this shape is a bell-shaped curve, and the PDF of sum of 5, 6, 10 uniformly distributed random variable approach a bell-shaped curve or a Gaussian distribution. Looking at the shape of characteristic function of sum of a few independent uniformly distributed random variables and seeing that it is approaching a bell-shaped curve is not a mathematical proof that sum of a few uniformly distributed random variables becomes a Gaussian random variable. We are going to cover the mathematical proof in coming lectures. In today's lecture, we introduce the idea of characteristic function, which has its roots in harmonic analysis and Fourier transform. By borrowing the idea of convolution integral and applying this idea to characteristic function of sum of two independent random variables, we found that characteristic function of sum of two independent random variables is equal to multiplication of characteristic functions of the two random variables used in the sum. We extended this idea to sum of n random variables, and for a special case of sum of n Gaussian random variables, we saw that the result is also a Gaussian. Then we saw that if we keep increasing the number of independent and uniformly distributed random variables in the definition of sum z, the shape of characteristic function of z approaches a bell-shaped curve, or it also becomes a Gaussian random variable. The truth is that no matter what the underlying distribution, if you add a lot of independent random variables to define a new random variable z, the PDF of z is going to approach the PDF of a Gaussian random variable. We'll continue to explore these ideas in coming lectures. Till then, I wish you the best. Thank you. Khuda Hafiz.